Alright, in this video we'll be going through the 2019 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. Sarah builds a simple guitar using a hollow wooden box as a resonator, and the 3 strings on a wooden fretboard. She fixes the strings between 2 bridges that are separated by 0.736 meters. In the space below, sketch the 4th harmonic or the 3rd overtone that is formed when the string is plucked. Alright, so clearly we don't have a very good image here, it's just grayed out, and that's obviously due to copyright reasons. NCEA can't keep it there for eternity, okay? But we should know that this is a guitar, and so therefore we're going to have a node on each end, okay? And because this is the 3rd harmonic, we're going to have a node in the middle, and node here, and then antinodes in between like so. And what this is going to look like is a wave sort of like this. There we go. We can confirm that this is the 4th harmonic because we know for the fundamental frequency of a wave where we have nodes on both ends, we know the length is equal to 1/2 of the wavelength. And therefore for the 4th harmonic, our length is equal to 4/2 wavelengths. And as you can see, we have 1, 2, 3, 4 half wavelengths, and so therefore this is our 4th harmonic. The speed of the wave through the string is 289 meters per second. Calculate the wavelength and frequency of this harmonic. Alright, so like I said in the previous question, our length is equal to 4/2 wavelengths, and therefore 2/4 times our length is equal to our wavelength. We are given a length right here, and so we can plug in that number. We get 2/4 times 0.736, and that's equal to our wavelength, and this gives a wavelength of 0.368 meters. Alright, and so that is the wavelength part complete. We also know that v is equal to f lambda, and therefore our frequency is equal to the velocity of the wave all over our wavelength. We are given the velocity of the wave, and we just found our wavelength, and therefore our frequency is equal to 289 divided by 0.368, and this gives a frequency of 785.33 hertz. There we go. The 3 strings of the box guitar produce different fundamental frequencies when played. Even though the strings are the same length and made of the same material, use the equation below to explain how this is possible. So as each string has the same length, and we know our length is directly proportional to our wavelength, if each string has the same length, then they must have the same wavelength for every given harmonic they produce. And we know that v is equal to f lambda, and so therefore as our lambda stays the same, the only thing that can change our frequency is the velocity. And so therefore, looking at this equation, each string is going to have a different tension, okay? So the more tension a string has, the higher the velocity, and so therefore the higher the frequency. Same thing in reverse, the lower the tension, the lower the velocity of the wave on the string, and therefore the lower the frequency. And you can write that in. Sarah wants to tune the D string to the frequency 147 Hz. She plays a 147 Hz tuning fork, then plucks the D string on the guitar. She notices a pulsating loudness twice every second. She gradually increases the tension of the string, then the pulsating loudness becomes less frequent and then disappears. Explain the phenomenon that causes the pulsating in loudness and why increasing the tension in the string makes it disappear. A calculation of the original frequency of the untuned D string should be included in your answer. Alright, so let's figure out the beat frequency first. We know that our frequency is equal to 1/t. And we are given that the pulsating in loudness happens twice every second. So this means that our period is equal to half, okay? Half a second. And so therefore plugging that into here, we get our beat frequency is equal to 1/half, and this gives a beat frequency of 2 Hz. And so therefore the original frequency of our D string, okay, is equal to 147 plus or minus 2. And so therefore we need to work out whether it's plus or minus. And to do that, we can go through our analysis of what is beats. So beats occur when we have 2 sound sources that are very similar in frequency, and because of their similarities in frequency, if we observe them from a fixed position, because the frequencies are slightly different, they're going to come in and out of phase. When the sound is perfectly in phase, that's going to result in constructive interference and therefore a louder sound, but when the waves are out of phase, that's going to result in destructive interference and therefore a quiet sound. And therefore, as they come in and out of phase, this results in a pulsating sound that goes from loud to quiet, loud to quiet, loud to quiet, loud to quiet. Now in here, it says she increases the tension of the string and the pulsating becomes less apparent. So if she increases the tension in the string, this results in the velocity of the wave in the string to also increase. And therefore, as v is equal to f lambda, and our wavelength does not change because our wavelength is directly proportional to our length, and our length hasn't changed, and so therefore our wavelength will not change. And so therefore, if our wave speed increases, therefore our frequency would increase. And so therefore, if we've increased the tension in the string, and therefore increasing the frequency, and then we don't hear beats, therefore our original frequency of D must have been 147 minus 2, and therefore the original frequency of our string D is equal to 145 Hz. Okay? Now let's confirm whether that makes sense. We had our original frequency on our D string, and we are hearing beats, so we increase the tension on the string, therefore increasing the wave speed in that string, and therefore increasing the frequency. And we keep increasing it until we no longer hear beats, and when we no longer hear beats, that's when we are equal to 147. And so you can write that all on. Sam and Miracle are experimenting with a 0.446 meter length of plastic pipe that is open at both ends. When the wind blows across the top of the pipe, Sam and Miracle hear a sound. They assume the sound is made by the air of the pipe resonating at the fundamental frequency. Show that the frequency of the sound is 379 Hz. Alright, so if we have a situation where we have a pipe that's open at both ends, okay, therefore we're going to have antinodes on each end and a node in the middle, and therefore this is our fundamental frequency. And as you can see, our length of the pipe is equal to 1/2 of the wavelength. And so therefore 2 times our length is equal to our wavelength. We are given a length of 0.446, so 2 times 0.446 is equal to our lambda. And this gives a wavelength of 0.892 meters. And therefore, as V is equal to F lambda, our frequency is equal to the velocity of the wave all over our wavelength. We're given the velocity of the wave as 338, and so that's 338 all over 0.892, and this gives a frequency of 378.92 Hz. And this indeed does round to 379 Hz. There we go. Sam places his hand over the end of the pipe and the frequency of the sound coming out of the pipe changes. Describe and explain the changes in frequency of the pipe. Draw diagrams to support your answer. Alright, so we're still playing the fundamental frequency. Again, we have our situation where we have a pipe that's open at both ends, and so our fundamental frequency looks like this. And as you can see, our length is still equal to 1/2 of the wavelength. However, for the case where we have a pipe that's open on one end and closed on the other, we're obviously going to have a node at this end and an antinode on this end. And as you can see, our length is equal to 1/4 of the wavelength. And so therefore we can rearrange and we get 2 times our length is equal to our wavelength for this pipe right here. But for this pipe, we get 4 times our length is equal to our wavelength. And so the pipe that is closed on one end and open on the other will have a greater wavelength. And because the velocity of the wave is constant, and also the length of the pipe is constant, therefore, as V is equal to F lambda, and therefore F is equal to V all over lambda, if this pipe right here has a higher wavelength, it is therefore going to have a lower frequency. Alright, and how much lower is it going to be? Well, we can see here that this is 2L and this is 4L, and so this wavelength is going to be twice as large as this wavelength, and so therefore the frequency of this pipe is going to be half that of this pipe. And we just found the frequency of this pipe, and so therefore this pipe has a frequency of 189.5 Hz. Alright, so the pipe that's open on one end and closed on the other has twice the wavelength of the pipe that is open at both ends, and so therefore it has half the frequency. And so you can write that all in words. Sam removes his hand so the pipe is open at both ends again. A strong gust of wind blows across the top of the pipe and causes a much higher pitched sound to be produced. Miracle uses an app on her phone to determine the frequency of the sound is 1138 Hz. Draw the new standing wave formed in the pipe in the diagram below. Identify the harmonic that is resonating in the air column. Alright, so we should know that Fn is equal to n times f1, where f1 is our fundamental frequency, okay? And also n is the harmonic that we are trying to find, okay? Alright, n is the harmonic that we're trying to find. Now, where this equation comes from, we should know that the frequency of our second harmonic is equal to 2 times the frequency of our first harmonic. The frequency of our third harmonic is equal to 3 times the frequency of our first harmonic as well. And so as you can see, we have our third harmonic and we times that by 3, and so n is the harmonic that we're trying to find. And we can see this equation is just a general version. Alright, we know our fundamental frequency f1 is equal to 379 Hz, and our fn in this case is equal to 1138 Hz. Okay? And so therefore rearranging for n, we get n is equal to fn all over f1, and therefore 1138 all over 379 is equal to 3.0026, which we can round to 3. And so therefore this is the third harmonic, or you can say it's the second overtone. Alright, there we go. Sam has the idea that if he holds the pipe while riding his bike really fast, he can recreate the same frequency in the pipe that the gust of wind had produced. Holding the pipe, Sam rides away from Miracle at a speed of 12.2 meters per second. Sam hears the pipe resonate at the frequency of 1138 Hz, but Miracle measures a different frequency. Calculate the frequency that Miracle would measure and explain why the two frequencies are not the same. Alright, so this is our Doppler effect. The reason why the two frequencies are not the same is because if we have Miracle over here and we have Sam over here, okay, and we can draw a dot for Sam's source, okay, as Sam is moving to the left, he is going to catch up to previously emitted wavefronts. So he emits a wavefront in all directions, but as the wavefronts in front of him move forward, he catches up to those wavefronts that are in front of him. And so what this causes is the wavefronts in front to be bunched up, but the wavefronts behind him to be spread out. And therefore, as these waves reach Miracle, she is going to perceive longer wavelengths. And as v is equal to f lambda, and the velocity of the wave does not change, right? The speed of sound does not change. Therefore, we can say that the frequency that she perceived is equal to the velocity all over the perceived wavelength. And as we just stated, the perceived wavelength is going to be greater than that of the true wavelength, and therefore the frequency that she observes is going to be lower than that of the true frequency, which is what Sam hears. And so we can calculate this frequency that she observes. We can use our Doppler equation, where we have the source frequency times the velocity of the wave all over the velocity of the wave plus the velocity of the source. Right, we're using plus in this case because the source is moving away from our observer, where our observer is Miracle and our source is Sam. Also, if you don't know where this equation comes from, I go through it in my first video on my Doppler videos in my Waves playlist, so you can go check that out. But plugging in our numbers, we get our observed frequency is equal to the source frequency, which is 1138, times the velocity of the wave, which is 338 meters per second, all over 338 meters per second, plus the velocity of the source, which is 12.2 meters per second. And this gives an observed frequency of 1098.36 Hertz. There we go. Lasers are used extensively in scientific research as they are point sources of monochromatic coherent light. In a lab, interference patterns can be demonstrated by shining a light through a diffraction grating and observing the pattern on a screen. The picture above shows 3 different colors, from top to bottom, violet, green, and red, of laser light shown through the same diffraction grating. Describe using physics principles why the violet maxima are closer together than the red maxima. Alright, so we know that n lambda is equal to d sine theta. Okay, and we should also know that red light has a greater wavelength when you compare it to violet light, which has a shorter wavelength, okay? And so therefore, if we use our equation, n lambda is equal to d sine theta, as they are shown through the exact same diffraction grating, our d value is going to be the same, and so therefore if our lambda value is greater for our red light, therefore our theta value must be greater, and so our maxima are further apart. Now for our violet light, using the exact same equation, n lambda is equal to d sine theta, once again, because we're shining the light through the same diffraction grating, our d value remains the same for both red and violet light. However, as violet has a shorter wavelength when compared to red light, its theta value must be smaller as well, and so therefore the maxima are closer together. And so you can write that in words. The diffraction grating of 400 slits per millimeter, and the angle between the center and second order maxima is 20.7 degrees for the violet laser. Show that the slit separation of the diffraction grating is 2.5 times 10 to the negative 6 meters. Alright, so the slit separation is our d value, and we know that's equal to 1 over n, where our n is 400 slits per millimeter. And so we can simply plug that in, and that's equal to 1 over 400 times 10 to the 3. The reason why we put it to times 10 to the 3 is to convert it from millimeters to meters, alright? And that's equal to 2.5 times 10 to the negative 6 meters. There we go. Calculate the wavelength of the laser light. Alright, so we know our n lambda is equal to d sine theta. We just calculated our d value up here. We are given our n value because we are measuring between the center and second order maxima. Okay, and so therefore our n is equal to 2. Our wavelength is what we are trying to find, and our theta value is given right here as 20.7 degrees. And so now we can just simply rearrange for our theta, and we get our lambda is equal to d sine theta all over our n value, and therefore our wavelength is equal to 2.5 times 10 to the negative 6 times sine 20.7 degrees all over 2, and this gives a wavelength of 4.418 times 10 to the negative 7 meters. There we go. In the marking schedule, it gives this answer, but then right below it, it says that the wavelength is equal to 442 meters, okay? I think this is a typo, and what they meant was 442 nanometers, okay? Just in case you got confused by that. So indeed, this is still the correct answer because this is the same as this. Explain the role of the diffraction grating and interference in producing interference patterns as seen when light passes through a diffraction grating. Alright, so when monochromatic light goes through a diffraction grating, okay, this is our diffraction grating right here, okay, as it passes through the slits, it's going to diffract, and therefore each diffracted light wave that goes through the slits acts as a point source. And so what it's going to look like is we're going to get thousands of these, okay? Obviously, I can only draw a few, but there's going to be thousands of them. Alright, and these waves are going to interfere with each other and they're going to reach a screen. When the waves meet in phase, and therefore the path difference is a whole number of wavelengths, we're going to see constructive interference, and this results in a bright spot, which we can call an antinode. However, when the waves meet out of phase, and therefore the path difference is a non-whole number of wavelengths, what we're going to see is destructive interference and therefore a dark spot, which we can also call a node. And this results in the interference pattern that we see on the wall, where we have points of maxima, which are our antinodes, and then dark regions in between, which are our nodes. And you can write that in. The wavelength of light from a green laser is 5.32 times 10 to the negative 7 meters. Describe and explain what would be seen at a point 28.6 degrees from the center of the green interference pattern. A calculation should accompany your answer. Alright, so for this, we're obviously going to use our equation n lambda is equal to d sine theta, okay? We are given our theta value. What we're trying to find is our n value, okay? If our n value is a perfect whole number, therefore we have reached a maxima, okay? So remember, our n value, if we have our diffraction grating right here, and this is our wall, our n value is our antinodal lines, okay? So this is going to be n is equal to 0, and then we have n is equal to 1, and we would have that on both sides, obviously. And this is our n is equal to 2, okay? And so if our n value is a perfect whole number, therefore we have reached a maxima. However, if it's anything in between, let's say 1.2, then that is falling within a dark region, okay? And so therefore the angle 28.6 falls within a dark region if our n value is a non-whole number, okay? So we can calculate our n value. We know our n is equal to d sine theta all over our wavelength, okay? We know our d value from before, and that's 2.5 times 10 to the negative 6. Our wavelength is given up here, and our theta value is also given over here. So now we can just simply plug in our numbers. 2.5 times 10 to the negative 6 times sine 28.6 degrees, all over 5.32 times 10 to the negative 7. And this gives an n value of 2.249, and therefore, as you can see, our n value is a non-whole number because we have a decimal place there, and so therefore this will fall on a dark region. And with that, we're done. See ya.